What if I told you that the angle of reflection is not always equal to the angle of incidence? Today, we'll answer all these questions in just 3 minutes by understanding the basics of quantum electrodynamics. Quantum means energy and electrodynamics means the interaction of electric current with the magnetic field. These phenomena could be explained by the interaction of electrons and photons, or rather virtual photons, because they do not really exist. They acquire their mass from energy, they interact and they disappear. Now let's say we want a photon to travel from a light bulb to a light detector. Now we start the stopwatch at the time the photon is emitted from the light bulb, and we stop the stopwatch at the time it is detected by the light detector. But if we do this consistently for the different paths a photon can take to reach the light detector, then we will find surprising observations. If we connect all the stopwatch needles from head to tail and then finally connect the head of the first needle to the tail of the last, then we will find the total probability of that event happening. To understand why light takes the path where the angle of incidence is equal to the angle of reflection, we'll see an analogy. Let's say it's NBA championship match and you have the ball in hand. All your team players are covered up and the opposition team is gathered at the center. Which path would you take to basket the ball? The total probability of an event happening can be found by summing up the probability of different paths. The stopwatch needles that we just discussed are nothing but vectors that have magnitude and direction. And when they were calculated for the paths at extreme ends, then the direction of the needles was opposite, so they got cancelled. And the direction of the paths in the center was similar, so they got add up. And this is the reason why you and even light is more likely to take the center path, where the angle of reflection is equal to the angle of incidence, and you also can score a basket. Tomonaga and Schwinger gave us intimidating and complex mathematical equations to account for the interactions between these electrons and photons. But Feynman, a great explainer and great bongo player for that matter, made these equations into cool pictorials now known as the Feynman Diagrams. These diagrams are as popular amongst the scientists as Feynman was amongst the ladies. Now to understand this diagram, we must know that the movement of an electron is given through a straight line and that of a photon through a wiggly line. Now in these Feynman diagrams, the action spots are places where the electrons emit or absorb the photons. Now these action spots more or less decide the complexity of the diagram. As the complexity of the diagram increases, its probability of contributing to the actual path decreases tremendously. This is no surprise why it is known as one of the most precise and consistent theories in the history of mankind, and well, the jewel of modern physics.